Graphical summaries, when we also study quantitative data in visual representation, because usually visually represented data is always preferred over, let's just say, a textual representation or a purely statistical representation. So we often go back to a lot of graphical summaries to really make our point when it comes to deciphering fundamental insights from numerical or quantitative data. So essentially, histograms are a type of visual representation where your data is put into bins and the frequency of data in each bin is represented. First, I'll give you an example from this particular code, and then I'll explain a little more in detail. So for the same data that we had, so this is how typically a histogram looks like. So as you can see over here, from the data set that we had, if I go back to the data set, right? So we had 35, 40, 45, 33, 30, 42. Now, if you look at the histogram, between 25 and 30, there are two observations. Rather, I'll show the ascending one. See, 25 and 30. Between 30 and 35, there are four observations: 32, 32, 33, and 35. Between 35 and 40, there is one observation, which is 35 only. And between 40 and 45, there are two observations, which is 42 and 45. Now, also what you will see, we'll look at something called as the boundary condition, because if you look at the bins, the, the first bin is from 25 to 30. Now it is showing two observations here. So it is including both the extremities. So it's taking 25 and it is considering 30 as well. So your next bin essentially considers all the data points which start from 31, which is why from 30 to 35, you see four observations. You have 32 two times, 33 one time, and 35 once. So total four observations. Now between 35 and 40, there is only one observation. So 36, 30. So essentially the bin from 35 to 40 considers data starting from 36. So 40 comes under that particular bin. And for the next bin from 40 to 45, you have again two observations. 45 is included in this particular bin. So this is how histogram works. It basically creates bins, and in each bin, it shows the frequency of the number of samples which fall in that range of the bin. Now, another important concept in a histogram is to understand skewness. Skewness is going to be extremely valuable at a later point of time in this course and also in all your future projects, because skewness determines a lot of fundamental qualities about the data. We'll come to all those aspects of skewness and how it affects the data as we move on in this curriculum. But first, I want to make you guys understand what skewness means in the first place. The histogram that you just saw right now, you can see that the number of observations in each bin are more or less equal, are more or less similar, if not equal, similar. But you will find instances where the histogram will be distributed in a way where there'll be extremely meager data in beginning, but the data is going to increase and you will see a lot of data points at the ends. Let me draw this a little better to make you understand. So you will see extremely less frequency here, but as the histogram moves forward, you will see extremely high frequency. Let me draw this once again. Extremely high frequency somewhere at the end. Okay. So essentially, if I just try and outline this particular histogram, it will come somewhat like this. So in this particular scenario, majority of the observations, they fall on the right hand side. This sort of a histogram is called left skewed. There is another case where majority of observations they fall on the left and slowly and steadily they decrease and you'll see very less observations on the right hand side. It is the opposite of what we studied previously. So when majority of observations fall on the left hand side, we call this right skewed. Okay. So the difference between left skewed and right skewed histogram and the way to remember it is to spot the tail. Now the tail is where there are less number of observations. So in a left skewed histogram, majority of the observations will lie on the right and tail is on the left. Similarly, for right skewed, majority of observations lie on the left. Therefore, the tail is towards the right. This is the difference between left skewed and right skewed histograms. Next, we'll move on to box plots. Box plots are another way to represent quantitative features. Now, essentially, what box plots show, it's a diagram like this. I'll elaborate on this a little more, but it will show you the 5-point summary. And the 5-point summary is exactly what we studied. The 25th percentile, the 50th percentile, the 75th percentile, the minimum value and the maximum value. This is how the 5-point summary looks like. But there is a subtle nuance in the box plot, which I'm coming to right now, because I need to also discuss the concept of outliers in a numerical data set. I'll go back to my WordPad and I'll just remove all of this. Now I'll draw something similar that you just saw in the R code. It is somewhat like this. Please forgive my drawing. Okay. Now in R, you will always see the box plot in a vertical fashion. To make you guys understand, I'll draw the same diagram horizontally. There is no difference, but it just makes it easy to understand. Right. So I'll just go over this diagram quickly. So first of all, we look at these three edges. This value right here is the 25th percentile. This right here is the 50th percentile. If you remember clearly, 50th percentile is also referred to as the median. This right here is the 75th percentile. This is called the first quartile. This is called the second quartile. This is called the third quartile. Okay. Now, there is a limit to which a histogram, sorry, a box plot can extend. These two lines are called the whiskers. And this right here, these represent the edges or the border values of a box plot. Now, this particular difference or this particular distance from the first quartile to the third quartile is called IQR or interquartile range. So I'll write IQR is equal to Q3 minus Q1. Now the extremities of this box plot is given by Q1 minus 1.5 into IQR and Q3 plus 1.5 into IQR. Okay. So the significance of this particular extreme values is that anything that lies beyond this is referred to as outliers. So if I have a point which is, let us say, greater than Q3 plus 1.5 into IQR, and it lies somewhere over here, then it will be an outlier. The significance of outliers in the bigger goal of machine learning is to basically analyze how points that are beyond the specific range of values, how do they impact the data set at large. I'll elaborate more on this idea as we go more in deep into machine learning. But what you need to understand now is this. For example, in a class, you will have majority of the students falling in a certain range. But there will be one or two students who will have significantly higher marks than the rest of the class. So those become important points of analysis when it comes to machine learning. How we treat them, how we analyze them, that's a different question that makes machine learning much more interesting. But for now, just understand this. Any point that lies beyond the extremities of the box plot is referred to as an outlier. For example, here in this case, if I change my earrings data and if I sort earrings, there is an observation 145. Now clearly you can figure out this 145 is in is different from all other data points, because all of the data points that fall in a certain range, 145 falls out of that range. You do a summary of earring now. You will get the max value as 145. You do a 5 num of earring. And again, you will get the same value. By the way, my bad. All this while I have been saying this variable name as earring, no matter what. It's earning. My bad, guys. Sorry. But fundamentally, if you look at the box plot, you see this point way outside the range of this box plot. This point is your outlier because it falls beyond the peripheries of the whiskers of the box plot, which is Q1 minus 1.5 into IQR, lower bound. Upper bound is Q3 plus 1.5 into IQR. So fundamentally, these are the different ways how you can graphically and statistically analyze your quantitative data. Now you move on to qualitative data. To analyze qualitative data, you have class frequency and relative class frequency, which basically tell you the number of times certain categorical data is repeated in a certain feature sample. Let's just say, for example, I have a variable called socks, and I have red, blue, blue, and green. If I give socks to my table function, then it will tell me that I have two blue socks, two red socks, and one green socks. So to analyze categorical variables, frequency becomes an important measure. And more than that, if you talk about graphical summaries, a great way to analyze your categorical variables is pie chart and bar chart. So let me just see if I can put a bar plot in socks. Pie chart looks something like this, where you have equal proportion of blue and red, and green has a slightly less, it has a lower proportion than both blue and red. And when it comes to bar plot, let me Google that as well. Again, in bar plots, I have to put my frequency value, not my categorical value. This is how a bar plot looks like. You have two observations of blue, two for red, and one for green. So with that, we come to the end of our first lecture. In the second session, we'll be continuing this topic and we'll be covering some more fundamental concepts of distributions. We'll start off with normal distribution and standard normal distribution. A lot's coming your way, so stay tuned and thank you so much for watching.